The famous Danish philosopher Søren Kierkegaard once observed that life can only be understood backwards, but it must be lived forwards. Now, what do you think he meant by this? And what does this have to do with differential equations and Bayesian statistics? Well, let's find out. Welcome to Dago.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. If you haven't used the differentialequations.jl package, you're missing out. Here's a benchmark of the differentialequations.jl package compared to other differential equations libraries written in other programming languages. In this table, anything in green is good, and anything in red is bad. The differentialequations.jl package is that column where almost everything is dark green. This means that not only is the differentialequations.jl package better than any other differential equations library, it means that no other competing library is even close. This is an extraordinary achievement, and is primarily thanks to Chris Rackauckas, who is the creator and lead developer. It's not hyperbole to say that the differentialequations.jl package is the greatest differential equations package to ever be created in the history of humanity. Okay, so maybe that's a little over the top, but it's a really good package, and you should definitely check it out. Full disclosure, Chris Rackauckas is a channel member, but he didn't ask me to say any of this. This is my own personal opinion. So what's a differential equation? A differential equation is an equation that defines how something changes with respect to something else. That something could be anything, and that something else is often time. So for example, velocity is how position changes with respect to time. And acceleration is how velocity changes with respect to time. Many of the changes that we observe in nature can be explained by some differential equation or system of differential equations. I have an entire playlist just for differential equations in Julia, so if you're interested in learning more, I provided a link to that playlist in the description below. In fact, I'm using one of the videos from that playlist, episode 708, as a source for this video. In that episode, I covered the Latka-Volterra equations, which is a system of first-order ordinary differential equations, also known as the predator-prey equations. In the interest of time, I've prepared a Pluto notebook to highlight some of the concepts that we'll need for today's tutorial, which will cover a Bayesian approach to differential equations. Here's the formal definition of the Latka-Volterra equations. There are two first-order ordinary differential equations, or ODEs, in this system. The first equation defines the change to the prey population with respect to time. And the second equation defines the change to the predator population with respect to time. In this tutorial, we'll be using rabbits as the prey and foxes as the predator. Since the equations are part of the same system, a change to the population of the prey will result in a change to the population of the predator. And a change to the population of the predator will result in a change to the population of the prey. And on it goes. The system of equations has four parameters, denoted here by the lowercase Greek letters alpha, beta, delta, and gamma. Alpha and beta are the population growth rate and decline rate, respectively, for the prey. Delta and gamma are the population growth rate and decline rate, respectively, for the predator. If you know the values of these parameters, then you can use the differentialequations.jl package to solve the system of ODEs. For today, we're going to use a package called ordinary_diffeq.jl, which is a component of the differentialequations.jl package. The ordinary_diffeq.jl package contains the core functionality that we need for today. When solving differential equations, the first thing you need to do is to translate the LaTeX equation into Julia code. Here's what a Julia version of the Lotka-Volterra equations looks like. Once you have a function definition, you need to set up all of the variables, which includes assigning beginning populations, assigning values for the parameters, and selecting a time span. Once you have all of that in place, you define the problem to be solved by using the ODE problem function. Finally, you solve the problem by using the solve function. In this solution, value 1 is the population of rabbits at any time t, and value 2 is the population of foxes at any time t. Here, we're using the SIT5 solver, which is a commonly used solver. But the differentialequations.jl ecosystem offers many different solvers that you can use. Once you have a solution, you can build an interactive model. In this interactive model, you can change the values for time, initial populations, and parameters. There's also a reset button for convenience. In the plot, the blue curve shows how the population of rabbits changes with respect to time, and the orange curve shows how the population of foxes changes with respect to time. As you move the time slider, you can see an animation of how both populations change over time. In the beginning, a lack of foxes results in the growth of the rabbit population. But the increasing rabbit population attracts more foxes into the environment, which leads to a decline in the rabbit population. A decline in the rabbit population leads to the foxes moving out of the environment to look for rabbits elsewhere. But then, the lack of foxes leads to a rejuvenation of the rabbit population. And on it goes. We won't be changing the initial population in our Bayesian model, but in this interactive model, you can change the initial population values to see the impact. And you can change the parameter values to see the impact. So this interactive model is great if you know the values for these parameters. But in the real world, you won't know these values, since they're unobserved. In the real world, you generally start by collecting observations over time. And then, once you have enough observations, you need to work backwards by building a model that attempts to explain your observations. There are several different methods for doing this. One method is a Bayesian approach. That's what we're going to do today. we're going to start with some observations. And then we're going to work backwards by building a Bayesian model that will try to find the values for the parameters alpha, beta, delta, and gamma that explains our observations. The main concepts for this tutorial come from a tutorial in the Turing.jl documentation. I provided a link to their tutorial in the description below. For the purposes of this video, I've modified their code. In the interest of time, I've prepared this code in advance. You can find a copy of my code in my GitHub repository. If you want to follow along, you can save a copy of this file in a tutorial folder on your computer. After you save the file, in VS Code, launch the Julia REPL by using Alt-J, then Alt-O. Change the present working directory to your tutorial directory. Enter the package manager by using the closing square brackets. Activate the tutorial directory. Add the following packages: CSV, ordinary diffie-q, statsplots, and Turing. Exit the package manager by hitting backspace. In the editor, execute the code to load the packages. For this tutorial, I'm using a random seed. Okay, now that we have our packages loaded, let's download some data. For today's tutorial, I've prepared some data that we can use. This file is saved in my GitHub repository, and you can find a copy of the URL in the description below. This code downloads the data off the internet and then loads the data into a Julia matrix. Click on the Julia logo icon and click on the table icon for the variable named data. This matrix has 2 rows and 101 columns. The first row shows the observations for the population of rabbits over time. The second row shows the observations for the population of foxes over time. These values are all integers greater than or equal to 0. Since you can't have 2.5 rabbits or negative 1.5 foxes. Now that we have our data, let's visualize it to see what it looks like. That TS variable is short for time steps, since this is time series data. This data covers 10 time periods with 10 observations per time period, for a total of 100 observations, plus 1 initial observation at time 0. So this plot sort of looks like the plot from the Pluto interactive model. But this plot is all jagged, since our observations are discrete integers, whereas the interactive model uses smooth continuous curves based on floating point numbers. The challenge here is to create a Bayesian model that can find the values for the parameters for the Latka-Volterra equations that will fit these observations. But before we can build this Bayesian model, we need to define the Latka-Volterra equations. The first thing we need to do is to define the Latka-Volterra equations using code that the ordinary diffie-q.jl package can understand. This is the same code that was used in the Pluto notebook. Next, we need to place the initial populations into a vector. This information can be found in the first column of our dataset. Next, we need to assign some values for the parameters. Since we don't know these values, we'll use a value of 1 as a placeholder for all of the parameters. These are the values that our Bayesian model will try to find. Once we assign values, we need to place these values into a vector of parameters. Next, we need to select a beginning time and an ending time that matches our observations. And then finally, we need to define the differential equation problem to be solved by using the ODE problem function from the ordinary diffeq.jl package. Here, the variable named prob is short for problem and not probability. Okay, we now have everything that we need in order to build a Bayesian model. I know that I went through this code fairly quickly, but this isn't meant to be a differential equations tutorial. Conceptually, the way to think about what just happened is that we defined something for our Bayesian model to use for the likelihood. For example, in earlier tutorials, we used a collection of straight lines, or a collection of sigmoid curves for the likelihood. This is the same concept. In this case, we're looking for a collection of differential equations. I'm going to type in the code for the model first, and then we'll talk about it after I'm done typing. Even though this model is longer than any model we've seen before, it follows the same format. As before, we need to define our prior beliefs and the likelihood. For the priors, we have the 4 unobserved parameters, alpha, beta, delta, and gamma. We also have a prior belief for sigma, which captures any unknown residuals. Because we don't know the values of the parameters, we're using weakly informative priors. That's weak as in W-E-A-K, meaning the opposite of strong. Weakly informative priors means that these prior beliefs do not provide much information for the model to use as a starting point. Instead, we're relying on the model to figure it out on its own. A truncated normal distribution is a normal distribution, but only using certain ranges within that distribution, which are defined by the lower and upper keyword arguments. Since the values for alpha, beta, delta, and gamma must be positive values, we set the lower bound at 0. Likewise, we also use a weakly informative prior in the form of a uniform distribution from 0 to 1 for the sigma parameter. For the likelihood, we start by placing the distributions for the parameters into a vector. In this Bayesian model, alpha, beta, delta, and gamma are not values. Instead, these are probability distributions, which are defined above. For the solution to the Latka-Volterra equations, we use the solve function from the ordinary diffeq.jl package. We're using the SIT5 solver, just like we used in the Pluto notebook. The SaveAt keyword argument is being used so that the solve function will return a solution that matches the time steps in our datasets. Finally, we use a for loop to fill a vector with normal distributions, using the solution to the Latka-Volterra equations as the mean. I know that it looks complicated, but conceptually, this model is the same as models that you've seen before in previous tutorials. Rather than looking for a collection of straight lines, or a collection of sigmoid curves, we're looking for a collection of differential equations. Now that we've defined our Bayesian model, the inference step is the same as we've seen before. We're using the nut sampler again and drawing 1000 samples. If you look in the summary statistics table, you can see the mean values for the parameters. It looks like Turing has found a solution. But how good is the solution? The standard deviations look okay. The r-hat values look good. Remember, you're looking for r-hat values close to 1. Now, what are those columns labeled ESS bulk and ESS tail? ESS is short for effective sample size. This is a measure of the number of effectively independent samples that were drawn. Ideally, all samples should be drawn independently. But due to the nature of MC-MC chains, not all samples are truly independent. ESS comes in two flavors, ESS bulk and ESS tail. ESS bulk is a measure of the effectively independent samples in the fat part, or bulk, of the posterior distribution. ESS tail is a measure of the effectively independent samples at the extreme ends, or tails, of the posterior distribution. As a rule of thumb, both ESS bulk and ESS tail should be greater than 100 per chain. With that said, these ESS numbers look fine as well. As a side note, the ESS per sec is just the ESS bulk number divided by the number of seconds that it took your computer to draw all of your samples. Just for the record, here are the parameter values that I used to generate the downloaded data. I used an alpha value of 2.0. I used a beta value of 1.2. I used a delta value of 0.9. And I used a gamma value of 2.9. So these mean values are pretty close. Let's visualize this chain to see if that sheds any further insights. so it looks like the posterior distributions have Gaussian shapes. But take a look at the trace plots. The trace plots look a little loose, and the mean values bounce up and down. So how can we tell if these parameter values match our observed data? One way to tell is by using something called retrodiction. Retrodiction is defined as the act of making a prediction about the past. That's what we're going to do. We're going to draw random samples from our posterior distributions, and then use those parameter values to solve the Latka-Volterra equations. We'll do that 300 times to see how well the solutions to the Latka-Volterra equations using those random samples fit our observed data. You can index the individual columns in a chain by using the parameter name as a symbol. The keyword argument replace equals false instructs the sampler not to pick the same sample more than once. We can view diagnostic plots for these posterior samples by using the plot function. So the probability distributions for our random samples resemble the posterior probability distributions, which is good. Let's use these sample values to solve the Latka-Volterra equations, and then add these solutions to our initial plot of observations. Remember, you need to call the name of the plot to view the updated plots. So that looks like a pretty good fit. How cool is that?
Bruh.
Now, I need to warn you, I ran this code multiple times without using a random seed, and Turing doesn't always find the correct solution. Since this is a complex model, and the draws are random, sometimes Turing will find a local solution that may not be optimal. Here's an example of a solution that Turing found that wasn't optimal. With this solution, all of the metrics in the summary statistics table look good, and the diagnostic plots look good as well. But clearly, this solution is incorrect. To avoid situations like this, it's a good practice to include retrodiction in your Bayesian analysis workflow to confirm that the solution does indeed fit your observations. Now, admittedly, the data that we used for this example was contrived data for the purposes of this demonstration. Real-world data will often be messier. But this example does show the potential of applying Bayesian analysis to a real-world situation. So we'll end where we started, with Kierkegaard's observation. Life can only be understood backwards, but it must be lived forwards. In order for us to understand the relationship between foxes and rabbits going forward, we start with our observations, and then we work backwards to define a Bayesian model, which ultimately discovers distributions for the parameters of the Latka-Volterra equations that generated our observations. Now that we have these probability distributions for the input parameters, we can use them to solve the Latka-Volterra equations. and use the results to understand the relationship between foxes and rabbits going forward. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, then please consider liking, commenting, sharing, and subscribing. If you'd like to support the educational work that I'm doing, then please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get ad-free, early access to all of my new videos. Thanks for watching, and good luck on your Julia journey!